Hey everyone, welcome back to the tools track. We have Darren Mothersele, who'll be taking us down the road of improving testability. I'm always banging on about testability at work, so I'm really looking forward to this one. Darren has been a software engineer for over 20 years and has created an open source programming language in that time. And the first programming language he learned was BASIC. So take us back. Not only that, but Darren is also an electronic musician. So make sure to check out his music on SoundCloud and other platforms. So over to you, Darren.
Thank you. Hi, everyone. So I grew up in the Peak District. If you don't know it, it's a really beautiful part of the UK. This road is called the Cat and Fiddle, and it runs through the Peak District, connecting the towns of Macclesfield and Buxton. It carries a lot of long distance traffic, lots of trucks, and also tourist traffic into the Peak District National Park. It's really beautiful scenery, but you have to drive really carefully or risk having a serious accident. It has had a reputation for being the most dangerous road in the UK. It's this continuous series of these sharp blind bends, and you've got hazards from oncoming motorbikes and trucks, and steep falls from the side of the road as it winds through the hills. While I was preparing for this talk, I actually found this article that says the Cat and Fiddle Road was in 2015 was no longer in Britain's top 10 most dangerous roads because of the implementation of various safety features, but it was mainly achieved through reducing speed and enforcing speed limits. So compare this to the Autobahn in Germany. Famously, the Autobahn has stretches of road with no speed limit, and so not only do these roads have much higher average speed, but they're also some of the safest roads in the world. It costs more than 800,000 euros per mile per year to maintain, but thanks to disciplined driving and investment in this infrastructure, you can go fast and stay safe. Hi, my name's Darren. I've been, as Lewis said, I've been developing software for over 20 years. I've worked on projects of all sizes in that time, and been on fast roads and very slow roads. So over the years, my attitude towards testing has changed. Obviously, I'm coming from a developer engineering point of view, so this talk is really about testing from that perspective. So hopefully, no matter what your particular role within testing is, that there'll be something in here which you'll find useful. But yeah, so over the years, my attitude towards testing has changed. I've worked on, to say, various different projects. In the past, I've worked on proof of concept code with no tests that somehow ended up running in production many years later, and I've gone into projects with legacy code of many years and worked to improve testability. I once had a recruiter ask me if I'd be okay working in an environment without tests, because he said they're a startup and they've got to move fast and they don't want to be slowed down by tests. This is TestCon, so hopefully I don't have to argue the value of testing. But unfortunately, I think today there's still a lot of people who believe testing can slow you down, and probably people have had bad experience with testing doing that in the past. So this road to improve testability is really about methods and things that I've seen that can work, that can improve safety, but not by slowing you down. So they actually mean we can move faster. So I'm on the engineering team at Peppy. We're building a health app. This app connects you to trusted information and real human experts. If you want to find out more about about us and what we do, you can visit peppy.health. So this is our road. This is the final destination that we want to get to. We want to be able to move fast and not break anything. But how do we get there? We've got a few stops along the way. And first, I want to think about what it really means to move fast and do that safely. So we've got, if you think about this in terms of like things that slow us down and things that help us accelerate. So over here on the right, we've got all the positive things that help us move quickly, and on the left, we've got things that slow us down. So we call these bugs and features. So if we're moving forward, we're delivering features, we're improving things. But on the other hand, if we've got to fix things, we've got bugs, then that's slowing us down. This is the visible part of what people can see. But there's also a side to this which is hidden, that's not visible, that you don't as easily see. And on the positive side, the things that help us accelerate, we call this architecture, and the things that slow us down, we call this technical debt. So yeah, if you're in an environment with lots of technical debt, then morale drops, output slows, and bugs appear out of the technical debt. And when technical debt is at its worst, you can fix something somewhere and something else breaks. And when it gets really bad, we spend more time fixing bugs and servicing the technical debt and less time delivering features. So in order to move fast and not be breaking things, we need to reduce technical debt, and we need to have a good architecture. So how do we avoid technical debt? Well, we can't, and we probably shouldn't. If we want to understand a bit more about what we mean by technical debt, Martin Fowler has this useful quadrant where he classifies technical debt into different categories based on whether it was prudent or reckless or deliberate or inadvertent. So sort of what this implies is that we can have deliberate tech debt. Debt isn't necessarily bad if it helps us move quickly, but there is obviously a type of debt that is bad and that will cause us issues down the road. So we have this sort of like ship now, deal with the consequences. There's this sort of deliberate, reckless, quick and dirty area, but we've also got tech debt that could arise out of lack of experience or just not knowing the right way to do it initially. But tech debt shouldn't really be an excuse for writing bad code. It's more about for me, I think it's more about this not knowing. It's about not really, we appreciate with development is that we don't really know what we're doing until we've done it. And it's by doing the work that we learn what we should have done and how we should have done it. And paying down technical debt is putting that learning back into the code. And when we have a lot of technical debt, we've done things, we've implemented them, we've got things out the door, but then the learning we've made in the process of doing that, we've not put back into the code. So we've not made the code easier to understand. We've not made it more maintainable. And really the learning is learning what the correct abstractions are, and that should be represented in the code. And when it's not, when we don't have abstractions, then we have a mess. And when we have too many abstractions, we have a mess. And when we have incorrect abstractions, we've got a code base that's difficult to understand, and it's hard to work with the code base. So getting to the right architecture is about having the right abstractions, and that's why paying off technical debt to getting to clean architecture are related. So what kind of architecture supports this sort of end goal of moving fast and not breaking things? What kind of architectural properties do we need? What do we mean by better testability? In a traditional layered architecture, typically you'd have a data source at the bottom, and then layers of abstraction on top of that. And then each layer normally depends on some common infrastructure stuff, the database, third-party API clients, payment processors. The problem with this architecture is that it sort of promotes coupling. You've got everything in one layer is dependent on the things below it, and everything, all the layers throughout are coupled to various infrastructure concerns. So obviously our systems wouldn't do anything useful without that infrastructure and without connecting into that infrastructure, but this introduces unnecessary coupling, and I think it's not the most ideal testable thing for complex systems. When I mean complex systems, what I mean is that we have systems that obviously have quite complex business logic that needs to be modeled, or just long-lived business applications, which they're going to be maintained for a long time. They need to have they need to exist for a long time, so they're going to have lots of changes made over that time. So that it's that complexity and needing to make changes that we need to account for. And we need to have a better separation of concerns. So for this, I prefer something called clean architecture style. There's actually a bunch of related architectures under this. So you can look up clean architecture, onion architecture, or ports and adapters, which is also known as hexagonal architecture. This diagram of mine is a sort of a simplification of all of them. And the key difference you notice is that instead of this being layered on top of the database, the database here exists on the outside, and not at the bottom. In fact, all the infrastructure concerns here are injected in from the outside. So the main benefit of this style is that it reduces coupling, because the code depends on abstractions and not specific implementations. So, for example, you could have an interface for a repository for loading and saving some entity which is defined in the core domain, but this just defines its behavior, and the actual implementation is injected in. So all the infrastructure concerns that exist externally, rather than being coupled to all the layers throughout the system. This is why this architecture style is sometimes called ports and adapters. The behavior is the port, and that's defined internally, and the actual implementation, the adapter, is injected in from the outside. So this massively helps reduce coupling. And with the dependency rule, where source code dependencies can only point inwards, each layer only depends on the layers inside of it. So this is a simplification. You may have more layers than this, but this is a good place to start. And you have the core domain in the middle, which is the business logic that's not specific to a single use case. This is dependency free. There's no dependencies. Like I say, you might have interfaces defining behavior as part of this, but they're not coupled to any implementation. Then wrapping that, you have the application services, which implement individual use cases. These wrap the domain layer and coordinate the various objects within the domain layer. And then outside of that, you then have infrastructure, which is then sort of injected in. So because of the dependency rule, by the time you get to this core business objects in the middle, there's no dependencies, and we'll see why that's useful for testability later on. So you can't avoid technical debt, and we probably shouldn't, but we do need to keep on top of it. We do need to reduce technical debt so that we can get to where we can move quickly and not break things, and therefore we need to be able to refactor. So we need to get to the clean code and the clean architecture. We need to be able to move quickly. This is Sisyphus in Greek mythology, who was punished in the underworld by Zeus in Greek mythology. He was forced to roll a boulder up a hill for all eternity, and every time he got near the top of the hill, the boulder rolls back down again. This is what refactoring feels like most of the time, because you can try to get to a clean architecture, you can try to reduce technical debt, but getting the ball to the top of the hill is really hard, and keeping it there is even harder. If you turn your back for a minute, and it can roll back down, things can end up worse than when they started. So that's why it's important to always be refactoring. It makes sense that if you view refactoring as putting the learning back into the system and making sure that we're implementing the correct abstractions, then it makes sense to be doing that as a continuous process. I say that the key to refactoring is to keep them small and to avoid the urge to change behavior. The key to success with refactoring is keeping it small and doing it often, not doing, waiting to do a big bang refactor when things get more risky. And also, refactoring is changing the code, improving the code, but without changing its behavior. So, we might do what we call drive-by refactorings, where we're implementing a feature or fixing something and we see an opportunity to improve the code. It's best to keep it as two activities. So, we might do it as an ongoing thing, but we're either improving the code or we're changing the behavior and not mixing up the two activities. So in order to be able to refactor, though, we need confidence. We need confidence in our ability to change the code without breaking things. We need confidence in our tests. We've got to have confidence in the tests to have that freedom to change the code and know that we're not breaking anything. But to do that, we need to have high value tests. So what do we mean by high value tests? What makes a test high value? When I first started writing tests, I was just thinking about protection. I was just thinking, these tests are here to protect us from bugs getting through. So, we have to stop bugs getting through to production. So, we write more and more tests. But, importantly, these tests also need to be maintainable. They also need to run quickly. A test is more valuable the faster it can run, because the faster a test is, the more often we can run the test, the more protection we're going to get, and the more freedom we get to be changing things. So if we can run the test multiple times as we're changing the code, then they can help us move fast and not break things. So optimizing tests for speed, I think, is important. They also need to be maintainable. We need to make sure that the quality stays high, that they're understandable, that new developers coming in can understand and read the tests as well as they can read the code. We need to maintain them so they represent the current state of the system, and we need to fix tests which are failing when they shouldn't. So removing flaky tests and fixing up the test, basically, so that they give us confidence, because we need to have the confidence in the tests to be able to do that refactoring. So this is the road we want to be on. This is the road which takes us through, improving testability. High value tests give us the confidence to refactor. We can keep on top of technical debt. We've got a system that's then easier to change, and we can then spend more time working on features and improving things, and have fewer bugs. But the reality is often different, and often we're not starting with a clean code and a greenfield project. Often we're starting from a system that does have technical debt, and there is this vicious cycle we can get stuck in between tests and technical debt. I see this as like a catch-22, where we can get stuck between having low value tests and technical debt and not being able to get out of it. Because on the one hand, we have the technical debt, which usually means we've got code which is hard to test. We've got difficult code to work with. Is usually, it's hard to isolate code to write tests for it. It's hard to automate end-to-end tests on it. And tech debt, it usually means it's, quite hard to understand spaghetti code, which makes it hard to understand where bugs are coming from. And, when something's changed, seemingly unrelated parts of the system break. When you combine that with low value tests where, if the tests are breaking every time we change something, the tests don't allow us to refactor. If we're not sure if a test is showing us that there's a bug, or if the test is broken, or we're not getting protection, we don't have confidence in them, the tests run slow, they're not maintainable, they don't cover the whole system, and we can't run them continuously because they take so long to run. So the tech debt has made testing hard, but also that's encouraged low value testing, which then the tests become hard to maintain, and so they become part of the tech debt problem too. So I sort of see this as a vicious cycle in the catch-22, which improving testability is how we break out of that. So what we really want to be on is this road to improving things and moving faster with not breaking things, but we want the right kind of tests which allow us to move quickly. We want high value tests, we want protection, the speed, and we want to be maintainable, so they give us the confidence. And we need to improve testing and testability together to get out of this vicious cycle. So we start by understanding, what are the right tests. So to understand that a bit more, I like to think of this in this way. We've got tests that either pass or fail, and we've either got bugs, or there's either a bug or there isn't a bug. If the tests fail and there's a bug, then that's a positive test. If the tests pass and there's no bug, then that's a negative test. We could also, if the tests are passing but bugs are getting through, then that's a false negative. But if the tests fail and there's no bug, then we've got a false positive, and this is not good. It could be refactoring that the test broke because it was too highly coupled to the implementation. Really, the test should be testing behavior, not the implementation. So, if the test fails, we know that the behavior is not matching what we're testing for, and it's not because the implementation has changed. It could also be a flaky test that sometimes passes, sometimes doesn't, and this is more damaging for our confidence in the tests. So another way I like to think of this is in terms of signal versus noise. So our confidence in the tests is very much linked to this ratio between signal and noise. We want less noise, fewer false positives, so that we can have confidence in the signal that we're getting, where a failing test is actually a bug. So here we have this represented another way. On the protection on one axis, we've got bugs getting through on one side through to catching bugs, or on the other side we've got low noise where tests failing, we're actually showing that there's something happening there that we need to be concerned about. It's not where there's a lot of noise, where tests failing mean that it might be the test that's broken, something in the implementation that's changed, that's broken the test. So where we want to be is here, where we've got low noise, where we can refactor the code, but we've got high signal, we're also catching bugs. So this is all well and good, but when we add in the third dimension of speed, because we want the tests to run quickly, during development, we want to be constantly running the tests. So we want high protection. We don't want false positives. We want to be able to refactor and change the code without breaking the tests, but we also want them to run quickly. And unfortunately, adding in 3 dimensions becomes a trilemma. We can only really optimize for 2 at a time. So if we think about this in terms of like a sort of, here's 3, choose 2 to optimize for, and then the trade-off, we have to understand the trade-offs there. So is, on the one hand, we've got is the test fast, or is it slow? Can we run it all the time? Can we run the test as often as we want to? Are bugs getting caught? Do we get the confidence from that? And are the tests not failing when we refactor the code? So obviously, at the bottom here, if we've got tests, the bottom question mark, if we've got tests that are fast and we can refactor the code, but they're not giving us any protection, then they're not really very useful. So this is the area that we are interested in. And what we're trading off here is we're trading off the speed of the test versus how easily we can refactor and change the code without breaking the test. So this sort of maps onto unit testing and end-to-end testing. I know when we start, this can end up in quite a heated debate. Some developers might prefer if I'd written integration tests there instead of end-to-end, depending on how you do them, where they'll sit. And I know the term unit test is often, sometimes debated what that means. So without getting into a sort of heated debate about that, what I'm really getting at here is that there is this trade-off between the speed of the test and how easily the test allows you to refactor the code without having to change the test. And that comes about, I think, because of you get the speed by isolating bits of code. So if you can isolate a bit of code to test it independently, then we're on the side of the unit tests. If the code has no dependencies, then that's easily isolated. That's very testable. If it's not, then we have to use mocks. And the problem with mocks is that they, by their nature, they lead you to coupling the test to the implementation detail. So that's why you move away from that sort of ability to refactor. If you use more mocks, you get to be able to isolate more, you get more towards unit tests, but you move away from from that sort of refactor ability of the test. But then when you use fewer mocks, you're integrating more of the system. So you're moving more towards end-to-end tests. So you're trading off the speed. So the more you integrate and the less you mock, then you slow things down eventually to end-to-end tests, which run the slowest. So what kind of tests are we going to get the most value out of? What kind of tests do we need to move fast and not break things? I think that's not necessarily the right question. I think it's more about what's the right kind of test for the right context. So, for example, we've got a use case we want to test and it might span multiple components. Then within the code, it makes more sense to be using an end-to-end test. But if we've got a highly important or complex logic, then we want to run those tests more often. If we can run those tests more quickly and run them all the time, then we're isolating the code, so we're more on the unit test side. So so I like to look at this from the code perspective. So I think of all code as existing somewhere on this chart. So we've got two axes. We've got, on the one axis, we've got importance or complexity. We can have complex code. We can have code that's mission critical, highly important to the business. All the code that implements these business critical invariants that can't be broken. That's what I think of as the sort of complex or important code. And then on the other axis, we've got the number of collaborators. So a particular piece of code will usually work with other bits of code to do what it needs to do. So this is what I mean by collaborative. So we're talking about what dependencies does this code have? What other bits of code does it use? How many of these collaborators does this code have to do its job? So you can imagine all code exists somewhere along these two axes. If you've got code down here, and there will be some code down here that's just trivial code. You know, it doesn't have many collaborators and it's not very complex. Then I'd argue that this code probably doesn't need testing. You know, it's obvious from what it is, what it's doing, and you know, my argument would be that test here probably doesn't need testing. But if you do have a lot of code that's in this area, then I'd suggest this is indicating there may be a problem somewhere else. You may not have the right, you know, the correct abstractions. It could be overly layered code or more complex architecture that's been sort of implemented for the sake of it. So yeah, although, you know, I wouldn't necessarily invest too much time looking at this particular part of the code base. You know, if there's a lot of this code, then I you know, potentially there could be something that, you know, that could be improved. As we move up this axis into a more complex code, then this is where I think unit testing is what, you know, we want to be using. So this is code, it doesn't have many collaborators, so it is easier to isolate it for unit testing, and it's very testable code because it doesn't have those dependencies. So it's very easy to test, and it's very fast to test that. So, you know, that's where unit tests are really the best thing there to be using. As you move up the axis with number of collaborators, this is where you need to start integrating. So I would prefer integrating over mocking, because, you know, as I discussed, mocking can tie your tests into the implementation, so they can make it less resistant to refactoring. So as you move up this axis and code has more collaborators and is you know, has more dependencies on other parts of the code, then this is where the integration tests and the end-to-end tests become the better sort of testing to be doing. But up here is the danger zone. So, you know, we might have code that's actually really hard to test. It's quite often, you know, I see legacy code, quite a lot of tech debt that built up ends up in this area. When code gets worked on more and more, you know, it eventually sort of can move into this area. Really, you know, in this area, this is where the code isn't very testable. So, you know, to make things more testable, I think the code needs to be, at this point, you know, split up and sort of worked on to move it out of the danger zone. You know, if the code has lots of collaborators and it's really complex, then, you know, it's really hard to test that code in a sort of efficient and good way. So yeah, how can we do that? What here, another way of looking at this is that, you know, is that we could see that, you know, if we can imagine code widening as it gets more collaborators, you know, it brings in more dependencies and has to coordinate the activity of more components, then, you know, we could see that as widening. And as code gets more complex, you know, we can see that as deepening. And what we really want is we want code to be either wide or deep, but we want to avoid making code that is both, that is wide and deep. And with existing code that's in that danger zone, it's already wide and deep, and we need to break it apart. And also, you know, there's a danger that code can move into that danger zone if we're constantly working on putting out more features, working on building on the code that we have without refactoring, without paying down the technical debt. Then more code will move into that danger zone over time. So what we really want to do is separate out the complex code from the coordination work that the code is doing. So this is really a separation of sort of algorithm from controller, and handily this maps onto that clean architecture diagram from earlier. So when we think about refactoring code out of that danger zone to improve its testability, we're also refactoring towards a more clean architecture style by splitting it into application service and core domain. So we have these dependency-free implementations of the business logic in the core domain, and then the application services that wrap around those coordinate the behavior of those activities and implement, logic specific to the use case, which is usually that sort of coordination logic between the collaborators, which sit in the layer below. And so again, then this maps onto that discussion about the trade-offs between the different types of the testing. So again, that dependency-free layer in the middle is perfect for unit testing, and then as we move out from the middle, we have to integrate more, eventually to the point where we've got code that's coordinating activity of lots of domains. The complexities in that domain, but that coordination code is then good for integration or end-to-end tests. So our road starts there with having higher value tests. This road to improving testability. These tests are the ones that give us protection, and they give us the confidence to refactor without breaking things. That allows us to refactor. That gets us into a position where we can be always reducing technical debt, improving architecture as we're working, and it gets us to a position then where we can move fast and not break things. So hopefully this gets us onto this road where we want to be on this road to improving testability, and breaks us out of that catch-22, that vicious cycle between low value tests and technical debt. So by having the high value tests, refactoring towards an architecture that improves testability, moving code out of that danger zone, to make it more testable by the right kind of testing, then we're improving testability, we're improving our tests, and hopefully that means we can then maintain the ability to move fast and not break things. So yeah, thank you. I finished a few minutes early, Lewis. Have we got questions? So yes, we've got some questions coming through.
We've got one question so far. So yeah, if you want to delve into this one, and hopefully some more questions start coming through.
Yeah, so are there techniques on how to evaluate technical debt other than static code analysis, like SonarQube? So SonarQube, these kind of tools are good, and I've used them in the past, and they can give figures and give data about what's happening, but quite often they don't tell you something that the developers they don't tell you things that developers don't already know. When the developers are working with the code on a day-to-day basis, they know where the tricky parts of the code are to work with, and so there is usually information in the team about like what's slowing us down, where is that technical debt that's causing us problems. On the other side of it, though, there is a problem that with the development team may want to fix everything, want to be working in this low tech debt environment, but some of that technical debt might actually not be a problem, because if there's some bits of code which are not ideal, they could be improved, but we don't need to change that code very often. No one really needs to work on that code. Then there's an argument that that's fine. So there are techniques there around things like looking at things like Git. So that there are tools out there which will look through Git and find where the hotspots are in the code base. What are the bits of code which change most often? So that can be places to look to sort of optimize what time you do have for paying off technical debt, which may not be very much, like to optimize that around where are the hotspots in the code. And then also to link it into sort of like risk as well, because, as the testers, tend to know what the riskiest bits of the code are. The testers are there. They, usually have the information about where bugs tend to be coming from more often than not. So, it's good to bring that information in as well. So, I think evaluating technical debt is just more than, a score of like how complex this code is, or, something like that. There's more to it than that. I hope that answers the question.
I think so. So question from me. So the journey looks great, and I think like this is something that I definitely endorse my teams to think about, is how can we extract that core and make the kind of component parts testable. So how do you bring people along for the journey? I think one of the challenges that I've faced is that people find it hard to extract what they currently have, and also the challenges of pressures from external dependencies.
Yeah, that's really, really hard, because particularly when you're talking about changing or moving to a different architecture or changing fundamental things about the code, they can have a wide impact and impact everything. I think it's not something that one developer can just go off and do on their own. And and I think that as one developer on a team, going off and writing all these tests in a specific way and trying to demonstrate this is the way we need to be doing things, can actually be detrimental in some cases, because you can end up with things that are very different to the way everyone else is doing things. So it really needs to be a team effort. And I think, like as I said, the usually on teams there is a will to get on top of the technical debt, but I think it's agreeing on how the team is going to do that, and then seeing the testing as part of that process, because implementing the right kind of tests for the code that you're changing. I think when you've got that view that the testing and the automated testing at least, and the way the code is refactoring, when there's that link between them, I think that's a good place to start, because you can then sort of focus the efforts on, if we split this code into sort of algorithm and controller, then we've got unit tests here, end-to-end tests here, and then there's a sort of focus for how the work can be done, and that could encourage then a cleaner architecture coming out the other side of it.
Yeah, nice. I agree. It's definitely a team effort. We've got another question. Would it help if QA was part of the development process already in the early stages?
This whole shifting left is something I'm very, very keen on. I think there's the saying, which I'm sure we've heard many times throughout the conference, that you can't inspect quality and you have to build it in, and that's I really believe that as well. Like, I think that working as a developer, it helps me to know what the expectations are up front, and to not have to make those assumptions myself. So conversations with testers before starting some complex piece of work, finding those edge cases, documenting that. Like, I'm not, I don't, fully, buy into the fully BDD way of doing things and working. But I do think there's a lot from the sort of process around that can be beneficial. So, having those conversations with QA before starting the work, and also the sort of rapid tests along the way. Like, if there's a checkpoint of like there's something to check, like just doing a rapid test on the developer's machine, just to get that QA involvement at the beginning, throughout the development process, and then obviously at the end. But yeah, the more weighted towards the beginning of the process, I think the better, to be honest.
Awesome. Cool. Any closing remarks? And you want to reference any content that you have?
No, I just wish people all the best, and hopefully, if something from that journey today has, sparked something, and feel free to hit me up on Twitter, or you can contact me via my website at daz.is. You can find me through there if there's any questions, or you want to, question anything I've said, or you can find me there.
Yeah, absolutely. The same goes for Anton, who did the previous talk. He's contactable via LinkedIn if you've got any questions that you didn't get answered as part of the talk. And I think one thing to call out, Darren has COVID, and he soldiered through with the talk, and you wouldn't have known. So really, really great stuff, man.
Thanks. Yeah, thanks for that, Lewis. Yeah.
Cool.